In this video, we will understand how the subharmonic injection method is applied to achieve 100% stator earth fault protection. But before we look at how the method works, let's understand why this type of protection is so important. The stator winding of a generator is grounded at the star point, typically through a high resistance, to limit earth fault current. But here's the challenge: if an earth fault occurs near the neutral, conventional schemes like residual overvoltage protection may fail to detect it. Now here's the real danger: if a second earth fault happens anywhere else on the stator winding, the grounding resistance gets bypassed. This causes a very high fault current, often in kiloamperes, to flow. And that can result in severe damage to the generator. That's why a reliable 100% stator earth fault protection is critical, especially for large generators. Now that we understand the need, let's explore how the subharmonic injection method addresses this. To implement this method, we need a few additional components: a low-frequency voltage source, a bandpass filter, and a miniature current transformer. A typical implementation of the subharmonic injection method looks like this. While this setup represents a commonly used configuration, there are a few other variations depending on the point of voltage injection or the relay used. In this video, we will focus on understanding the key working principle using this standard configuration. Now, let's walk through how this setup works. To minimize the influence of system capacitances, this method uses a 20 Hz square wave voltage source. The voltage is injected into the neutral grounding transformer, NGT, through a bandpass filter and a load resistor. It's recommended to keep the load resistor greater than 0.5 ohms where possible. To do this, choose a high secondary voltage rating for the NGT. 500 volt is a practical and commonly used value. The bandpass filter performs two important functions. First, it smoothens the injected square wave signal. Second, it protects the 20 Hz generator from excessive feedback currents, particularly during a terminal-to-earth fault. Let's now see how the system behaves under normal and fault conditions. Under normal conditions, the injected 20 Hz signal flows through the surge capacitors and the stray capacitance of the stator and step-up transformer windings. When an earth fault occurs, even close to the neutral, an additional current path is created through the fault resistance, RF. So now, the 20 Hz source drives current through both the capacitive path and the fault path. The relay continuously monitors two key values: the voltage across the star point, measured across the load resistor or a voltage divider, and the current flowing to ground, measured using the miniature CT. Here it's important to highlight one common mistake. Many engineers think they can measure the driving voltage directly at the output of the 20 Hz source. But that's not correct. For accurate measurement of the driving voltage, and to correctly calculate fault resistance, this voltage must be measured across the load resistor or the voltage divider, not at the source. So, two separate cables should always be used, one for injecting the 20 Hz signal and another for measuring the actual driving voltage. From the measured voltage and current, the relay calculates the 20 Hz voltage and current phasors. It then derives the complex impedance of the path, and from that, determines the fault resistance RF. Under normal conditions, the calculated fault resistance is very high. During an earth fault, the resistance drops significantly. Typical relay settings might be 3 to 10 kiloohms for the alarm stage and 1 to 2 kiloohms for the trip stage. These values ensure the system responds accurately without nuisance tripping. In addition to the fault resistance thresholds, the relay may include the following settings: stator ground over current pickup, voltage supervision, and current supervision, etc. We will cover these relay settings and more in a separate video. Before we wrap up, let's quickly recap what we learned today. The subharmonic injection method uses a 20 Hz signal injected into the neutral circuit to detect earth faults reliably. It works even when the generator is offline or at standstill. It requires a 20 Hz voltage generator, bandpass filter, and a miniature CT with suitable configuration. The relay calculates fault resistance from measured voltage and current to detect earth faults anywhere on the stator. And finally, avoid a common mistake: don't measure voltage at the 20 Hz source. For accuracy, always measure across the load resistor or the voltage divider using a separate cable. If you found this video helpful, don't forget to like, share, and subscribe. Thanks for watching, and see you in the next video.